Thank you very much. So I'm Chris Kiekintveld. I'm currently an associate professor at the University of Texas at El Paso, right along the border between the US and Mexico. So I've been interested in AI for more than 15 years. My interest in cybersecurity is somewhat more recent. But like many of you here, I've been really fascinated to think about the implications for all of the advances that have been made in artificial intelligence and how those might apply to cybersecurity. So as I was thinking about my comments for this talk, I was thinking about, well, what are the challenges and opportunities that come from all the rapid advances that we've had in AI, especially in this context where we don't necessarily fully understand how all of these advances are working in artificial intelligence. We don't understand how robust they are, not just to uncertainty, but to malicious attacks on these systems, as we've heard throughout the day on the context of adversarial learning. So of course it's impossible to come up with an exhaustive list of the opportunities and challenges that this brings, and such a list would be obsolete next year in any case. But one thing that jumped out at me was the duality of some of these challenges and opportunities. So all these AI methods are potentially applicable both to defense and to offense, right? So our attackers are facing the same fundamental issues with applying these technologies as we are. And if we think about that, that actually leads us, in some cases, to thinking about some of these technologies in different ways. So one example is the capability to do rapid dynamic deception, so making fast changes to configurations and so forth. And on one side, that could lead to new opportunities to disguise malware, to try to evade intrusion detection systems. On the other side, we have work that's being done in the area of moving target defense, where we look at making changes to our network infrastructure or other configurations to try to make it difficult for an attacker to do accurate reconnaissance and be able to plan effective attacks. We've heard a lot about this problem of AI being a potential attack surface. As we integrate more AIs into our decision-making process, these AIs themselves are now a potential attack surface, using things like adversarial samples against these systems. However, as I'm going to talk about, if we flip this on its head and look at it the other way, an adversarial example might be an effective decoy that we could deploy against an attacker. Finally, our AIs are going to have to interact with humans, both on the defense and on the offensive side. It's not just going to be humans, it's not just going to be AIs, it's going to be complex teams that are functioning together in different ways, and this leads to, again, both challenges and opportunities. Humans are unpredictable. This is one of the biggest challenges in designing a lot of AIs is that they have to interact with humans. And modeling and understanding how humans might react in different situations is fundamentally quite difficult. However, humans also have exploitable biases. So in certain cases, this might allow our AIs to exploit the biases and limitations of humans in ways that can help in cybersecurity. Okay. So I want to frame much of the rest of my talk in the context of work that we are doing in the area of cyber deception. So this is the overall motivating diagram for a large project involving collaborators from many universities that's looking at improving our capabilities for cyber deception. And in particular, we have these three P keywords along the bottom. Pervasive, persistent, and personalized. So we don't just want simple one-off instances of cyber deception. We want deception that is pervasive, that is acting across many different layers of different types at different levels in the decision-making process, that is persistent, not just a one-shot, one-off deployment, but again, acting in the long term over time and reacting to when attackers might learn about certain deception strategies that are being used to make those adaptations less effective. And finally, personalized. So being able to do more detailed attacker modeling, and based on what we know about attackers, being able to target and personalize deception strategies against different types or perhaps even different individual attackers. So towards this end, we have a lot of research that's going on on all of these different areas that you see here. So we have work on attacker modeling, where we have collaborators from psychology and cognitive modeling. We have work at the systems level, where we're looking at how do you actually generate and deploy deceptive strategies at the systems layer, but also how you, it's called forcing the attacker into the light here, but you can think about this as detection, but also how you set up your systems to enable you to do detection. And the area that I'm most heavily involved in is this box of cyber deceptive game theory, where we think about using game theoretic models to make use of behavior predictions for the purpose of optimizing how we use these deception strategies. So to give a somewhat more concrete example, a lot of our work has been motivated by this idea of dynamic Honeynets. So of course, honeypots and other kinds of simple deception strategies have been around for quite some time. What we're thinking about here is maybe the next iteration of that, where we are thinking not just about deploying a one-off honeypot and seeing what stumbles into it, but how do we use these things strategically? How do we make them more effective? How do we use not just honeypots, but other kinds of honey objects, honey tokens, honey files, perhaps honey users, in a more comprehensive kind of deception strategy? But then also, how do you make this dynamic? How do you make it take into account observations of the attacker and evolve your deception strategy over time based on that? And this has led to a number of different research questions that my research group has addressed. This is a good thing when you have lots of motivated PhD students, is to have lots of different kinds of questions. So these involve things like, how do we optimally place honeypots in a network? How do we do these dynamic responses to observations about the attacker? How do we evolve or generate more effective deceptive objects? How would we use deceptive objects to learn more about attacker goals and capabilities? If we have some personalized attacker models, how would we target deception strategies at them? And finally, how do we prevent attackers from learning about our deceptive strategy and evading it? I'm going to talk a little bit more about a couple of these topics. So first, I wanted to acknowledge that we have a long line of work using these game theoretic models to think about how we optimize deception strategies. And this includes actually a lot of collaborators from the Czech Technical University that we worked with over a number of years, including a few papers that I have listed here from one of our previous speakers, Karl Dakota. So we've done a lot of work in this area. I'm not going to talk about it much here, just except pointing out that we've done it. A lot of this work assumes that we have some effective deceptive objects available to us. And that's what I want to talk a little bit more about next. So this is interesting in part because it ties into a lot of the discussion that has been had today about adversarial learning. So if we think about what a deceptive object is and what the purpose of it is, or we could also think about camouflage as another variation of this, we're really trying to defeat attempts at classification. A simple example of that is real versus fake, although classification more generally could have, we could be trying to prevent somebody from detecting what the real type of something is, and trying to confuse them about multiple categories of real objects. So the interesting thing here is that we get to play the role of the adversary. So in most of the previous talks, we've talked about generating attacks on machine learning algorithms and generating these deceptive samples. Well, here, when we are generating the deceptive objects, we get to play what's been talked about as the easier role. So it's often thought of as easier to create these adversarial samples than it is to defend against them. So here we get a chance to turn that on its head, and we are trying to defeat the attacker's means of classification now instead of the inverse. So we are also interested in applying game theoretic ideas to this same kind of problem, and I'll talk a little bit about how these interact in a moment. Again, to put this into a somewhat more concrete context, one of the specific problems that we're looking at right now is on traffic obfuscation and the creation of deceptive honey flows, or deceptive network traffic objects. So the obfuscation problem is thinking about an attacker who's trying to look at network traffic and do classification. So perhaps classifying different protocols or different kinds of activities. and how we could modify the patterns of traffic to make it more difficult for an attacker to accurately do traffic classification. Honey flows, that's again an instance of this. To create an effective decoy network traffic flow, you'd want to be able to create one that's going to defeat attempts to classify it as real or false. There are also interesting strategic questions about what do you do with honey flows and how do you use them effectively that can be addressed through game theoretic models as well. We've seen a number of examples of this kind of slide throughout the day. So the standard adversarial sample story. Here we have a pig, so we've got a different animal than some of the ones that were shown earlier. The idea, though, is the same. So we've got some object, and we're going to add some perturbations to that to cause a classification error. Okay? So people have started doing some prior work actually thinking about applying this idea to network traffic to defeat classification attempts on network traffic. Interestingly, so this does seem promising in the previous work. They've been able to show some results, but they run into this problem that was talked about a bit earlier in the case of trying to do adversarial learning for malware evasion, which is that when you start thinking about some of these problems, you run into this issue that there are more complex constraints and costs on how you can actually do the modifications than is true in something like just an image, right? So in an image, the typical assumption is that I can arbitrarily modify the features and modify the different pixels of this image, and there's not real complex structure to the constraints there. And a lot of these cybersecurity examples, including this work on traffic modification, the structure of what you can modify and how hard or how costly it is to make those modifications is actually quite a bit more challenging. And I want to talk about this in the context of a simple stylized game model that we have developed that tries to capture some of what's going on here at a very basic level. So this is an instance of what we call the feature selection game. And it's a very simplified model. We have just two objects here. One is real and one is fake. And the attacker is basically trying to determine which is the real object and which is the fake object. And the defender does not want the attacker to correctly identify the real object and attack it. And each of these objects is associated with a feature vector here. Again, we're keeping this very simple, so we just have two binary features in this example. So each object is going to have either a 0, 0, 0, 1, 1, 0, or 1, 1. And these probability distributions here for the real objects and the fake objects describe sort of naturally how similar or how dissimilar they appear, without any modification or obfuscation attempts by the defender. And the cost functions down here describe how costly it is for the defender to make modifications to these features. So the idea is that both players are going to know all this information in the game. The defender gets to observe the actual features that are generated by nature according to these probability distributions, and then can make some modifications, can flip some bits in this case to try to disguise either the real object or the fake object to make it more difficult for the attacker to pick the right one. Okay, so the attacker gets to observe the modified feature vectors and select a target to attack, and basically he gets a positive payoff if he picks the right one, and a negative payoff otherwise. And of course, one of the key features of the model is these probability distributions, and they basically represent how naturally dissimilar or similar the objects are. If they're very similar, perhaps even the same, then the defender doesn't have to do any work. It's naturally very difficult to tell these things apart. If the distributions are very different, then the objects naturally look very different. There are many ways, of course, to characterize how similar or dissimilar probability distributions are. This idea of an earth mover's distance is one of those, where we basically look at how many changes you need to make these distributions look similar or dissimilar. So there's a number of kind of questions that we can ask even of this simple sort of model. And one thing that we were very interested in was this idea of one-sided versus two-sided deception. So a lot of work on deception assumes that you're going to try to make a decoy object or a deceptive object, and you're going to modify its features to look as much as possible like a real thing. And that's what we call one-sided deception here. Two-sided deception incorporates this other option that we have of actually modifying the real objects as well. So we can have real objects that are modified to look more fake in some sense. And we would think that that would be perhaps quite helpful. So these real objects are now trying to disguise themselves among the fake ones in some sense. So this is an initial simulation that we did. So we have the Earth mover's distance over here. So these are real and fake objects that naturally look very similar. These are ones that naturally look very different. This line represents the defender's payoff with no modifications at all. The top one is with two-sided modifications, and the bottom one, or the middle one there, is with only modifying the decoys. And so we see that the deception is effective at confusing the adversary. What's a little bit surprising is that these two lines are so close. We see a small advantage here for doing two-sided deception, but not a very large one. So we were a little bit confused by that. But then we started looking at the interaction between these similarity and dissimilarity metrics with the cost functions. And what we found is that what really matters is the asymmetry of the cost functions in addition to the dissimilarity of these underlying distributions. So here we have an extreme case where one of the features is unmodifiable, and it's a different feature for both the real and the fake systems. And in this case, we see a quite dramatic difference where the two-sided deception is really critical to being able to do effective deception in this case. So another thing that we looked at was the assumption that the attacker is going to be perfectly rational. In the previous results I showed you, we adopted this sort of standard game theoretic idea that we're going to have a perfectly rational attacker who knows everything. At the other end of the spectrum, we might have a perfectly naive attacker, someone who just takes these feature vectors at face value and behaves according to what they see. They don't do any sophisticated reasoning to try to figure out what is the probability that this one is real or fake. So these two top lines here add that case for both the two-sided and one-sided deception. And these other lines are the same ones that we saw in the previous graph. So the naive attackers predictably do much, much worse. There's a consistent advantage here for two-sided deception across the entire spectrum. But the most interesting thing is actually over here. So because these attackers can actually be led astray, in a perfectly rational model, the attackers can never be led to believe something false. Here, because we have limited attackers, we can actually get them to believe something false, and deception is very effective even in cases where the natural objects are already close to indistinguishable. So that really motivates us to think about what are the right assumptions. Should we be thinking about attackers who are perfectly rational, perfectly naive, or more realistically, somewhere in between? Okay. So we're interested in expanding these games. So we're actually looking at how we can find perfectly optimal strategies for small instances of these games, but also how these kinds of games can inform adversarial machine learning approaches when we look at larger and more complex cases. Okay, so I want to shift gears here a little bit and talk about another aspect of the problem, and that is how our AIs are interacting with humans. So, of course, our AI systems will be interacting with humans, both benign and malicious, and this leads to a lot of challenges for them in terms of how they can predict human decision-making, and also how we can design AIs that are robust to these kinds of unpredictable behaviors. It also leads to some interesting opportunities, and an interesting way of framing this is as an adversarial human factors problem. We've spent decades in computer science thinking about human factors and trying to make systems usable, making them user-friendly and easy for people to use. When we're thinking about attackers, we should be doing exactly the opposite, right? We should be making it as hard and as frustrating and as difficult as possible for attackers to achieve what they want to achieve. And there's decades of literature in psychology and social sciences about the kinds of limitations and biases that people have. These include, for example, things like confirmation bias and sunk cost fallacies and so forth. So the idea of adversarial human factors is, let's take these limitations that we know in the humans that we're facing and try to exploit them and turn them to our advantage. So I want to talk about a little bit of work that we've done with humans on the context of attacker learning that tries to get at some of these ideas. So the starting point here is that long-term deception is going to require that we are able to deceive attackers over a long period of time. We don't want them to be able to learn our deception strategy, figure out what we're doing, and evade it. So we actually, in collaboration with some of our psychology collaborators, designed a laboratory game that we could run with human participants playing the role of attackers in a simple Honeypot selection game. So the attackers have to play this game, and they have to pick nodes that they are going to attack, and they're going to do this over 50 rounds, so they get the opportunity to learn what's going on in this game. And the defender is choosing some subset of these nodes to be honeypots, and he's got a constrained budget, so he can't choose all of them. And the question is, well, how effectively are humans able to learn this deception policy? Are there different kinds of policies that are going to be harder for humans to learn? And eventually, can we model and predict the learning dynamics? Can we say, based on a computational model, what are the likely strategies that a human might choose in the next rounds? So we did our initial experiment with a few different deception policies. So one is a simple pure strategy, deterministic policy. It's greedy, we set it, and we leave it alone. The next one is based on a game theoretic analysis where we found an equilibrium solution that gives us a randomized policy, and that randomized policy stays fixed. So an attacker can potentially learn the probabilities that each of these nodes is going to be a honeypot in each round. And the last one is based on an algorithm from the machine learning literature called LLR. The important thing is that this one is adaptive, and it actually is learning and responding to what the human attackers are doing over time. And here's an initial result. So we're looking at the performance of the humans in this learning task over time, over 50 rounds here. The bottom line here is the pure strategy deterministic policy. And we see that the humans are very reliably able to learn this policy quite quickly. These lines represent regret, so lower is better. 0 would mean that they are always choosing the best thing they could do. So we want them to have high regret. And the pure strategy does very poorly in that regard. The humans are quickly able to figure it out and essentially are best responding within 5 to 10 rounds. The other two policies, what's interesting here is that they are almost flat, especially the adaptive policy. The humans, even in this quite simple deception game, have learned almost nothing. They are very confused about what's going on, and they have a difficult time figuring out what the strategy is. They're a little bit more effective at learning against the fixed equilibrium policy, but not that much more so. So this is interesting in one sense because it at least gives us hope that by changing things up and keeping our defenses moving, we can mitigate this potential for people to figure out easily what we're doing and best respond to that. The next part of the work, though, is perhaps even more interesting. Here we're trying to come up with models that will predict what the humans will actually do in the next round. Okay? And we have a few baseline models, but then we have two interesting competitors here. One is a machine learning algorithm drawn from the multi-arm bandit literature called Thompson sampling. And another is based on our work with the psychology collaborators, drawing in their expertise in cognitive modeling. And they have a model called instance-based learning, which has been used for a couple of decades now in modeling human performance in learning tasks. So I've got a bunch of graphs on this slide, and I'm not going to describe them all. The pattern, though, that you should see is that these graphs look fairly similar. And to make a long story short, both of these approaches are actually surprisingly effective at predicting the round-to-round behaviors of the human participants in these games. We can get a pretty close match between these fairly simple behavioral models and how humans are learning in this deception task. And of course, our next task that's actually ongoing is looking at how we can take these models and actually calculate a game theoretic response to them and actually optimize our behavior against the humans. Okay? So these are a couple of examples of where our work fits in with adversary behavior predictions and generating deceptive objects. There's a lot more work in getting this entire cyber deception idea up and off the ground and actually implemented in real systems, and we're excited about pursuing that over the next couple of years. And I'm going to leave you just with an image of some of my students who have actually participated in doing this work. Of course, we have many other collaborators who have been instrumental in collaborating on these topics as well. These are 4 of the students that have played the biggest role in this work on cyber deception to date. So thank you very much. I'm happy to take questions.
Thank you, Christopher. Slido time. Please ask questions. I have one.
Sure.
If we look 5 years ahead from now, and your presentation title was about challenges. What will be the challenges 5 years from now? How do you see your presentations 5 years from now here on this stage?
Well, that would certainly require a crystal ball. So I think I said at the beginning of the talk that this list would probably change even in a year from now, much less 5 years from now. So I do think that we are going to see the increasing integration of these AI technologies, especially machine learning and deep learning, into our systems. And we are already starting to put them into roles where we are giving a lot of trust to these systems that we cannot fully explain and cannot make perfectly robust. I don't think that that's a challenge that's going to be solved by next year or even 5 years. So I expect that we will still be talking about that as an important issue.
Which part of the network could consider as deceived to be changed periodically?
Okay, so I'll take this as a question about what are the kinds of things that you could change as part of a deception strategy. And this is an area where there's a lot of opportunity for creativity. So I mentioned classical honeypots, deploying a server or a host or something like that on the network, and that's maybe an easy one. But there's a lot of other opportunities for doing deception in different parts of the space. So I talked about network traffic as an example, using perhaps fake credentials that are designed to be intercepted by an adversary, fake users, fake accounts. Can't think of any others off the top of my head, but there are many of them.
No more questions? So thank you, Christopher. This was
Thank you very much.
Brilliant. Thank you.